with his education starting in China, Shanghai Jiatong University. Then he did a master's degree at ETH Zurich, Switzerland. PhD at the University of Washington, and then most importantly, he did a postdoc at MIT, and Leeds as well. And now he's an assistant professor in Earth and Environmental Engineering, with an appointment in electric engineering as well at Columbia University. And he'll educate us on energy storage in electricity. So we'll be happy working on
thanks, Alden, for the introduction, and yes, very happy to be back and also be in this new building. And yeah, today's topic is energy storage and equilibrium. So, primary point, previous subscribe was mentioning about withholding, but that was the older version of abstract. But as I give this talk here and there, I think people have very mixed opinion.
Never mind, don't worry about what I said.
No, I just say actually this is one of the point. This study is withholding a good word or bad word for battery. I think that's actually
we were very curious about that.
Yeah. But I can talk about it. So just to get the background out of the way, yes. Am I hearing a that's not this? Oh, it's okay. Okay. So we do see there's a very significant a change in the battery development or after 2020. Okay. So before 2020, you see here we barely have anything, but after 2020, we start to see the battery capacity grows significantly, led by California and Texas, right? And these two number changes on a quarterly basis. The newest data shows California has 13 gigawatt of battery, and these are grid-scale batteries that actively participates in the electricity market. Texas 10, okay. So yeah, and also if you think of the drivers, it's the California, ERCOT, and also part of the WEC except California, okay. Yeah, and if you look at the development of the battery over the past 15 years, we see we went a long way to arrive here, and started somewhere in 2010 to 2015. Battery at that time were still expensive, okay, and the deployments of battery are experimental, so it's mostly frequency regulation, and the battery are small and 15 to 30 minutes duration. So duration is a concept used often by battery engineers, meaning if you have a fully charged battery and you discharge it at a rated power, how long does it take to fully discharge battery, right? So the shorter duration, meaning the relatively the energy capacity is small compared to the power rating. And we have a small battery, only like 0.5 gigawatt. And after 2015, this battery start to go up a little bit, but still mostly providing ancillary service. And it's really after 2020, we see, per the previous figure, there's a surge in battery capacity. So now the battery reaches 2 hour to 4 hour duration, right? You see the duration start also go up as the battery gets cheaper. And also we have a 30 to 50 gigawatt of capacity. And most of data showing that arbitrage, the participating wholesale energy market, is becoming the main service of battery, which makes a lot of sense because if you think about ancillary service market, it's a small market, right? If you think about California, we have 13 gigawatt of battery there. We have to do in the energy market, right? So now we have this many battery in the electricity market, and for those of you who might have studied the electricity market, we know this is actually a very dedicated market, and the fundamental concept with electricity market, or actually any market, is we want the market to maximize short-term welfare. So by competition, right, in the market with efficient market design, the fees from resources should converge to their true physical marginal costs, right? And that means maximizing short-term welfare, optimal allocation of resources, right? And obviously in the past, when we talk about resources, mostly thermal generator, and this means that the true bids should converge to the fuel cost of generators, right? If you think of a thermal generator, it's heat recur plus fuel cost, right? And vice versa, a fuel cost should also serve as a baseline for quick design and also market power monitoring, okay? But this question is much more complicated with batteries, right? Battery being arbitraging energy or price differences, it has much complex cost factors, right? So basically, for the rest of the talk, I will present a few studies we did related to these topics. First, we want to show that how does the current market design works with batteries, right? With the equilibrium, how would the battery form equilibrium in the current market design? And then we also talk about more about how would battery participate in the current market environment, and also mention some of our recent applications in real world industry. Okay. Right. So the first study I want to talk about is basically following this line of thought, like how would the current market work once we have a lot of batteries, right? So first, this is a very kind of high level model, right? For electricity market in the United States, we have a day-ahead market and real-time market. Day-ahead market is a forward market, clear based on the forecast of demand. Real-time market is the spot market, clear some realized demand. Okay. Yeah, and also one of the fundamental idea with day-ahead market, it also schedules slow generators, right? The generator have a startup, ramp rate constraint, etc. They have to be scheduled ahead of time. Many are too slow to respond in spot market, right? So based on this framework, this is the work led by Jerry, who was actually a business school student in Columbia, and worked with me on this work, graduated, and yeah, and now is on his way to go to Yale to do his faculty job. So we derived this framework to model day-ahead and real-time market equilibriums, right? So we model the demand. We consider a two-period example with peak demand and off-peak demand, right? And we consider them to be jointly distribution, right? And then the day-ahead are the expectation of this demand and the battery decision. In this case, right, there are 4 decisions. So this is basically a two-period, two market. So in total, 4 time steps framework. Okay. And also we model this varies on the battery can do charge and discharge, and also we consider a very simplified state of charge constraint in this two-period example. That means there's sum of decision have to be 0 in this. Okay. So based on this framework, okay, we derive the market equilibrium model. So we do it separately for day-ahead market and the real-time market. So one key here is we separate generators into 2 groups, the fast generators and the slow generators, right? So the fast generators, the slow generators, or say both fast and slow ones, GS and GF, get scheduled in day-ahead market. So their generation are the function of the day-ahead price. And then see here are the battery decision. Well, in real-time market, we assume the slow generators follow their day-ahead schedule, where the fast generators can reschedule based on the real-time market. Okay, so the blue one, the PRT, is the real price. Of course, the battery also gets a chance to reschedule from their day-ahead set point. Okay. And we use KF to represent the ratio of fast generators in the system. Again, we can analytically also derive the inverse supply function here. Okay. So based on this framework, Jerry, we proved many properties, which I'm not going through all of them. For example, there's some property on different distortions. There's one property which I'm not showing here, but it's like battery prefer real-time market compared to regular generators, which is also intuitively understandable because the real-time prices in the spot market, prices are more volatile. So battery like to arbitrage more volatile market, right? But I think the most important property that we proved, which also relevant to the rest of this talk, is the market still converge to social, converge to a efficient equilibrium with more batteries, right? So the way we do it here is we define a price of anarchy, which is basically the same concept to market efficiency, but I think this term is more often used by business school people. But it's defined slightly different. So we have the baseline cost, which is generator cost without batteries, versus here is with the generator cost with vertically integrated battery, which is the social welfare maximum dispatch of the batteries. Okay, and the ratio on the denominator is the generator cost with battery of the total cost as an outcome of battery market competition, right? So this POA, the larger the POA, meaning the market, it's so the denominator has a larger value, which means it's less efficient, and POA of 1, meaning we achieve the same efficient dispatch to the social welfare maximum outcome. Okay, so the one thing, one more critical result here, we show that POA is, under the competitive equilibrium is bounded based on the number of the battery in market, right? Of course, here we assume they are the same batteries, right? It's bounded between the ratio to n over so 1 over n square, worst case, and 1 over n to the power of 4, best case. Okay, so this does show that, of course, this is based on this two market. Two market is realistic. Two period, which is less realistic. But it's based on this framework. It does show that the more batteries there are, the market will converge, and at a faster rate, at a relatively faster rate, to efficient market. And we also show that this POA also decreases with the share of the fast generators. I see the question.
Yes.
Okay, I can stop you.
Sure.
Yeah.
Can I ask, so maybe I missed it. So when you say generator cost for vertical, what is the battery doing there? Is it optimized in real time, or
yeah, it's optimized by the system operator.
but in real time, not for anything to do with the day. The day ahead is already done, and then in real time.
Both day ahead plus real time. Yes. Yeah.
But then is there still deviations between?
Yeah, based on realized demand. Yes.
Even for the social planners battery.
For the
So like I didn't understand in real time.
Yeah.
When the social planner operates the battery,
yeah.
it is just to minimize cost.
Yeah.
But then is there any way it is using the day ahead
No, I think
decisions in the vertical?
no. Well, in real time, it does not consider the day ahead decision, but the framework does also schedule the battery in day ahead. Yeah.
And that impacts the prices for the slower generators. That
It does impact the slow generator. Yeah, but the battery, because it's flexible. Yes.
So basically, you assume that the slow and fast generators, they are competitive. There's no strategic
No. Yeah.
interaction, but the batteries are strategic.
Exactly. Yeah. Which is
That's why different title.
Sorry?
That's why withholding.
Yeah.
The question from Salah. Any intuition of why this ratio is topology independent, no transmission aspects?
Oh, here we didn't actually, in this case, we haven't talked about
Very
topology.
important.
But if you think about topology, it will definitely narrow the competition of batteries. So this ratio, I'm not sure how, we didn't really look into topology. I'm not sure how we change the ratio, but it will cause battery to more, it will definitely decrease the efficiency. Yeah.
I guess there is a complicated question to that one. If you have topology, then the locational price is all different already. So people don't get paid uniform pricing. They get paid locational.
Yeah.
And pay locational.
Yeah.
So topology is not just making the difference in where you can deliver it from what, but this interpretation of the results, if you are uniform price, you can do uniform price or pay as bid with and without topology change. And I think that the answers are different. That's what I'm trying to say. Because when you have congestion, you always have LMPs difference. So just to double check my sanity, if you have LMPs, there is no more uniform pricing, right? People get paid whatever LMP is. Yeah, so that jump from pay as bid to uniform and other way around, and its impact of topology on that, if you've taken into consideration or not, is, I think it's huge actually, but it gets neglected.
Yeah, you mean practice battery. I think the topology even has a much more critical role in battery investment, right? And all this developer, when they build battery, they try to build the battery at the most congested part because.
Right. So that's, I think, that part, I think, Laura, that's not.
Yeah.
So everything gets paid in uniform pricing?
Yeah, there's no congestion. Okay. Single bus. Yeah.
With the intuition between the worst that what which conditions cause worse versus best?
I think so. So here definitely the good point. First, let's talk about the intuition between fast generators. Is because you think about a battery, they are fast. So batteries, and in this framework, because only the fast generator can get rescheduled and the battery in the real-time market. Fast generator, there's more competitor to the battery. So I would, I haven't really checked this mathematically, but my intuition says the best case should have 100% fast generators. You have all the slow generator and the battery have more freedom to play the games. All right. Yeah. So this is the work I think personally I really like this work. I think this is one of the first work that rigorously show that even with the current market, with more batteries, there's still a way to converge to the social welfare maximum. Okay. So now.
Sorry, can I ask? So here you show like in the short term you reach an equilibrium solution, but what about the long term, including investments?
Yeah, that we did. Yeah. I think investment is the third stage. Product. Actually, one of my students now is doing this plus a capacity market, which is then
closer.
Yeah. This is the first one. So we show that at least the market is good for batteries. It's not ideal, but so now I want to present some of the work. Actually, this spawns all the way when I was back with a postdoc here at MIT. On how do we develop algorithm for insurance arbitrage energy market? Right. So competition is beneficial. The current market mechanism is sub-ideal for storage. So the energy market, especially real-time market, is not a truthful market for storage, and this was highlighted by some of the paper from our from the community. What does it mean? The truthful meaning, if you are thermal generators, right? Of course, there's a room to play some games, but for the generator can simply say, I don't want to play any game. I just want to submit a true cost to the system, and the system will give me a fair return, right? I'm not expecting to make a lot of money, but at least I want to make back my fair return, right? So this is the truthful market. But apparently, battery cannot do this, especially in real-time market, right? If you think about real-time market, a simplified model is it clears every hour, right? And it only clears this hour. However, for battery, because of SOC constraint, the battery need to consider what happens in the future, right? So either in the arbitrage or in the bidding strategy, battery have to consider future possibilities, okay, and future opportunities into now, which basically the opportunity cost, right? Actually, this concept was long acknowledged by Bill Hogan from Harvard. I think in 2001, he wrote a note on withholding mechanisms. And at that time, he does make a note. Of course, the most of the manuscript was talking about how do we identify withholding, how withholding is bad. But there was some notes here that if the unit is energy limited, we cannot apply a typical withholding mechanism, market monitoring to that unit, aka the market does not allow energy limited resources to act honest. Okay. Of course, at that time he was mostly referring to natural gas, liquid natural gas. Okay, storage. Yeah. So this is actually, so the storage here must use strategy and other method to indirectly manage their SOC and future opportunity and also degradation. And this is a non-trivial problem. And this was really highlighted by companies in this field like Bolun, which is a joint venture between Siemens and AES. I guess everybody knows Siemens, but AES is one of the major battery developer in the United States, saying the current bidding approaches cannot handle the complexity with batteries. Of course, the next is we are using AI to solve this problem, right? So if you wonder what do they mean here, so at least, of course, I don't know what they actually do is their trade secret, but at least in this talk, we'll talk about some of our understanding of how you can use algorithm and AI to base storage in this field. So let's first look at kind of the minimalist arbitrage formulation. And this is a deterministic version, right? Actually, if you look at the battery arbitrage formulation, it's very simple. It's actually very simple. The most important thing is the first term, it's the price, right? That's like the price and then the discharge, right? So if you discharge, you make money, right? You make profit. If you charge, it's like you buy in some energy, of course, minus the cost of discharge, right? So here the cost is mainly reflecting battery degradation. So theoretically, it could be also on the charge part, but what actually do, because this battery is cycling all the time, the degradation is really measuring cycles. So my personal preference, I would like to put the cost mostly on the discharge. So it's a battery model is more aligned to generators that when you discharge, you have a cost, right? And then we have a charge discharge power limit P, and then storage energy balance with efficiency, right? And especially here, whenever battery charge or discharge, you lose a little bit energy. And actually, what's this problem most complex, which is a seemingly very simple constraint, the energy capacity, right? We have very limited energy capacity. That means we have opportunity issue, right?
Oh, can I ask clarification question? When you do this optimization over time, what is the definition of withholding?
Oh,
because it's temporal, it's not one snapshot at a time.
Yeah, exactly. So withholding here, meaning the battery is not, the battery does this, but if you look at market clearance in real-time market sequentially,
right,
we see the battery is not discharging at a particular time interval despite its meter cost.
But do you evaluate that like 1 T at a time or over the entire time? I think you.
I think
that is a huge issue. I think.
Yeah, I think this is also the point made by Dale Hogan that if you really want, the entire concept is the withholding of battery or energy limited resources. Is really you need to look at a window of time.
Yes.
Not a time instant. But all the current concept is built on one time instant. But what makes a window of time complex is there uncertainty.
I think you have the same question there from Saurabh. Can you read it?
Saurabh said, I guess the question is, what is benchmark for withholding behavior?
Yes.
And there is, well, we can obviously do a hindsight optimal dispatch, but that did not consider uncertainty.
Okay, so that to kill this one to the end, there is no one paper that I could find on the definition of market power when you think things over time. This is really
this was one of the work I was going to talk about, but then I feel it's a bit too much and not that, but so I remove it. But we did write a recent paper about basically, or we have a series of paper. Basically, the conclusion is for a power system operator, you cannot 100% claim a battery is exercising market power. There's no ground.
Right, right.
Yeah, we cannot say it.
No, but we don't, I'm sorry, I'm not an economist, you guys know better, but market power for electricity has never been defined. You just say you have to build certain marginal cost.
Yeah.
And that is, I don't know what it is.
Yeah, I think for a thermal generator, we have been using fuel cost, right? And we can define if you are so much different than your true fuel cost.
Over which time? And for storage is important time. I think this is completely ill-posed.
But basically, we ended up with a solution that we can enforce a bid bound, reasonable bid bound for batteries on this issue. So basically, system operator saying I cannot tell whether your withholding is legit or illegit, but based on my model, I can say that maybe $200. There's no reason for you to offer more than $200 based on all the uncertainty model I have. So that's what I work. But it's really there's no way we can.
It's not rigorous, right?
It's no. And as Sarah mentioned, there's no benchmark.
Yeah.
There's no fair benchmark.
Yeah, thanks a lot. So I'm wondering, what the cost to go?
We haven't talked about next page. Yeah. This is just like a simple deterministic version.
Paper to us for with your withholding.
Yeah. I didn't expect people. So that's in all the previous talk, I think people were like, I still didn't really get the withholding part. So, but I didn't expect.
Doesn't there have to be a limit? How about charge and discharge? You said that you impose a $200 limit. That's for this charge, I guess, but don't you have to have a limit for charging as well?
We didn't, of course. Mathematically they are symmetrical, but I think in practice people were more concerned with discharge because that, or in the data we see that's the one that can go.
But increases the price.
Increase the price. Yeah. Okay. So this is the kind of the problem, and or the biggest problem here is the price is uncertain, right? We have a lambda here, and just give you guys or for those of you who never saw electricity price, this is like kind of what a typical electricity price. And this is not a very, it's actually from New York City. I think that this is May probably 2019. So this is like pretty okay. In the spring, not too hot, not too cold, but still, due to local congestion or Manhattan is, New York City is congested. So we do see the price like this. So this shows the complexity with this. Okay. And what has been done to battery, we have 13 gigawatt battery or like 50 gigawatt battery now. What people have been doing? There's not the best solution. So all the solution exists, of course, for the industry folks, MPC or MPC type method is the most welcoming method. Okay, is that it predicts prices first and run optimization. The best of this thing is intuitive and can be modularized. If you are a battery developer, you can totally buy prediction from a third-party company, and your batteries, right? So you can insert in my battery and do it. Very convenient. But as I later mentioned, that this really depends on price forecast, and if you want to also generate market fees from this, it may not be very trivial. Okay. Reinforcement learning is also another space, and of course, this was more explored by academics. It's flexible and data-driven, right? But limitations, one is encoding capacity and degradation constraints, and externalities is a bit challenging. There's a way to do it. Actually, I think that some of our earlier papers, we propose some tricks, but it's not very reliable. Also, the biggest problem that this is really why industry or a lot of feedback we heard from our industry friends is they don't like it because they cannot say anything. They want interpretability. especially if you think of them, they want to be able to explain to their boss why I ended up losing money today, right? I need to explain that. Stochastic dynamic programming is the kind of the fundamentalist, zero-rate fundamentalist approach. It provides a fundamental benchmark, but computation has been an issue. Okay. Yeah.
Excuse me, are you talking about centralized formulation that you showed? This is just at the bidding level.
Yeah, this is just
These are different formulas.
This is the arbitrage level.
Yeah, so.
Yeah.
Oh, so it's just individual, sorry.
Yeah, this is the
Yeah,
other
sorry,
individual
yeah.
variables. Yes. Yeah. So here actually for the rest of the talk we focus a bit more on the
Individual.
individual batteries. Yeah. So here actually our work, the work we propose starts from a stochastic dynamic programming reformulation with so this is the value function now, right? And the value function is recursively defined from the value function from the next time period, right? Okay. And here it's a variable function. Real-time price here depends on the previous real-time price and also the data price, right? So you look at some simple data analysis, you see the real-time price of this particular time period is mostly depends on one, the day-ahead price of the same time period, and also the real-time price from the previous time step. Okay. And then we can characterize the empirical distribution by simply take bunch of price, 3-4 years of price data, do a conditional distribution, and we get this, right? And then we can discretize it into price node using a stage 1 Markov process, right? In which case, the day-ahead price sets the distribution mean, and then the uncertainty nodes are depending on the yesterday's real-time price. On the previous time step real-time price, right? So based on this, this is actually the work I did with Bolun when I was here, that we derived a fast algorithm to update the value function directly based on the price distribution F. You see here, and this is the derivative, right? This is the derivative of the bigger of the value function. You can call this the marginal value function, right? Can be directly updated based on the value function from the next time period, the CDF of the price distribution function, and all this, cost, efficiency, everything we know. So everything this, if you just do a backwards calculation, we actually know everything here, right? And they are also looks a bit complicated. They are just conditional expectations. So this actually computes very fast. Okay. So based on this, we move this with our Markov stage 1 Markov process model, right? And we can derive basically stochastic, a fast SDP solution to arbitrage battery and the performance is very well. I think in this case this is 20 price node, right? So we assume for every time step, every 5 minutes, we discretize the price into 20 nodes. And to do a full year simulation, this is about 100K steps. It just takes less than 100 seconds. Okay. It's from the entire solution, from calculating value function to simulating, right? Of course, simulation is quick, but even for calculating value function, it's very fast. It's pure data driven. Yes, the distribution of lambda t is pure data driven. Actually, this is a good point that I think I didn't hear. The one problem is because the price is discrete, we may run into issue that there are missing parts, right? If you're doing conditional distribution, right? There could be missing parts on the price. So we need to do actually one trick we need to use is do some local smoothing on the density function, because we have to condition it on previous. If we just do stage independent, we actually, the price data is okay. But if started to price dependent, so the price distribution of this time period condition on the price realization from the previous time period, we run into a data problem. We have a lot of missing links because we just never have this data appeared in the history. So we have to do some local smoothing. That's the point.
May I ask, so the price is the only variable. There's not other conditioning variables.
The price, yes, yeah. So one thing people run into in the past when doing SDP is they discretize both the SOC and the price node. So you can easily end up with the 2 or 3 states, and then this dynamic programming the states flow. I think one of the main thing here we show is we don't need to discretize the state, the SOC, but just to treat it using piecewise linearity. So just pass it directly as a function.
For example, if I know the hour of the day, I would condition things differently than if I was just doing an unconditional distribution based on the price.
Yeah, hour of the day. Correct.
And if I knew that it was windy because we're experiencing a front of weather, and the wind was likely to continue over 3 days, I would have a different conditional distribution.
So correct. So the most helpful trick we did here is the expectation of the real-time price show the center on the day-ahead price. And if you think about the day-ahead price, it already contains a lot of information on whether it's a weekday or weekend, right? Because it already cleared based on the demand forecast. So we show that in this case, there are 2 things that help us most in bootstrapping performance. This is the profit ratio, so how much profit I can capture compared to knowing the perfect price prediction, right? So stage independent, and we only categorize real-time price distribution will give us around 50%, considering dependency between 2 stages, right? So my current price distribution depends on price distribution from the previous time period, give us 10% more. And if I also further condition it also on the day-ahead price, right? So my current price distribution not only depends on the previous period, but also depends on the day-ahead price, give us a further 10%. So that's, so I think a lot of information, we did try some weekly pattern and seasonal pattern that helped a little, but not much, but we didn't figure things, probably because all those information already boiled into the day-ahead price.
This may be, I know this is not what you're doing, but if you wanted to incorporate another market in here, would this type of algorithm be able to, if you had a kind of, if you're tracking 2 markets simultaneously, would you be able to do something similar, or does that kind of?
I would say, given this model, probably it's better just to train a different type model for different market.
Okay.
One work that related to this, but I didn't include in today, is we can also include a neural network to directly do some prediction of the V here. And that case, if you integrate that with transfer learning, then you have basically, I think in the case study, if we train the entire neural network using neural data, then we did a transfer learning to the Australia market. It actually worked okay. But for this model itself, there's no guarantee how the performance will if you move to another market.
Well, I meant more in the sense of if you have access to, if you're doing energy trading, and then you also have access to like another energy market simultaneously somehow, or another one of those sets of services at the same time. Can you could you extend this model to participate in multiple markets, or does it only really work if you're in one market?
If you're talking about multiple markets in the same location?
Yeah.
Not directly. Directly, this will still be a real-time price arbitrage, but we do have another work looking at joint trading also in the day-ahead market. This could be useful. Has one of the as part of the solution, but it's not. We never tried to directly address it into this part. Not a holistic solution. So yeah, so this is this one. Also, they did the work, and now it works as a Baltimore utility. So Next is we can further enhance this model by considering nonlinear battery characteristic. And this is really showing up if you start going from grid-scale batteries. In grid-scale batteries, they are LFP batteries, mostly. They have actually very stable voltage dynamics. Actually so good that it's causing the problem with battery health diagnosis, because all these battery diagnostic techniques or battery state estimation techniques depends on the voltage slope, okay? But if you move on to, let's say, distributed battery, in case battery are more likely to be nickel cobalt, NMC nickel cobalt based batteries, they have a stronger voltage dependency when the voltage here is SOC. So, and if you generalize it with SOC and efficiency, this is basically degradation, discharging charge power, they look like something like this. Especially, if you have an electric vehicle, they have EV has CCCV charging. So, Tesla basically saying if you plug in, I can charge your car very quickly to 50, 60%. But for the rest, I need to charge it slowly. That's exactly what's happening here based on battery dynamics. So what do we do with this, right? So we can actually, in this case, we can represent them in our formulation as all these factors depends on the SOC, right? They are now a function of E, right? So now this is becoming nonlinear, and also we never really rigorously proved this is non-convex, but I think it's also a little bit non-convex here, but we didn't really try to prove it. But we can actually extend our algorithm to this setting because our algorithm is based on first order of normality, so derivative, so we can do some local smoothing to some local derivative, right? You can still get all the derivative out of this. So we can actually extend the previous algorithm into this version. So now you see, now it has all the derivative here. Of course, took the student quite some time to make sure this is right. But this actually we test this with of the other benchmark is we just use a mixed integrated program to do it. It's also or not really correct. But the two achieved a similar result, but obvious and on the deterministic case, not stochastic. And this one computes much faster than the mixed linear program. Okay. And based on this, we did a case study. So Joshua did this study. Now he went back to his home in Panama to work on EV coordination. So basically, we are using this algorithm. So if you think about the V2G or unidirectional, it's arbitrage problem with a terminal energy condition. If you think about V1G, right, it's unidirectional, is you set the discharge power rating to 0. So the same algorithm can be totally used for V2G coordination, but also here we have a capacity constraint, and we combine this with this least laxity first scheduling algorithm with I think it was initially originally proposed by Cartech to manage this, and also we use the Cartech data set and show that in both cases under the stochastic setting we achieve pretty close result compared to the perfect forecast benchmarking we had in V2G, and of course this one is the unconditional uncontrolled battery charging. Okay, so just to show this algorithm can be attended with nonlinear batteries, with coordinating a large amount of battery fleets, with still retains computation efficiency. Yeah, so that's the two work. We actually I will circle back to this concept on the value function later, but this just to show that the value function, if you go back to the original principle, the value function is a way to derive, understand battery. And if you go back to the withholding discussion, this is the source of why battery withhold is you have the value function cost function, right? So V is the cost, and the cost is based on the future, and you have this cost, which one will never be able to fairly judge it because it has uncertainty. Everybody has a different forecast of uncertainty, and that V is the source on why battery is withholding in practice. Yeah. Question.
For these two STP books, when you're simulating the market outcome, is the algorithm outputting goods in terms of quantity terms or in terms of the quantity?
This case, this is only quantity, but we will talk about quantity pairs next. Yeah. Okay.
Also the detailed battery characteristics. Where do you get that information from? These curves.
I think there are some open data set on the battery testing, but yeah, well, to be fair, this is from a cell, not from the pack level.
Right.
It's from a single cell. But I think the general idea is for EV batteries, because the cells are NMC and also the BMS are not designed to do grid arbitrage, so it's definitely more restrictive compared to LRP grid scale batteries. So next, I will actually talk about something on price, what we did on price prediction, and we eventually where we ended up with some industry solution, right? So we talked about the value function, but the price prediction is still, the value function didn't consider price prediction directly, but price prediction is in practice still the most important thing to do for battery, right? They are critical for bit design, learning features. So and even you think about the SDP solution, we can totally design our stochastic process center around our price prediction, right? In that case, our uncertainty is modeling the price prediction error, right? So in all these cases, price prediction is very important. Okay. Now the default way to predict prices is your neural network, but neural network is focused on smooth string, because it has a norm 2 minimization. But if you look at battery, single batteries, battery doesn't really care about average price. They only care about price peak and valleys because it's arbitrage price differences, right? So this is one example. You see, of course, not the best we can do, but just so if you just use some off-the-shelf RSTM network to predict prices 5 hours ahead. So at every time we predict the price 5 hours, right? If you do 5 minutes ahead, of course, the price prediction will be very good, but 5 hours, the battery to design bid, you need to look into the future, right? To quantify its future opportunity. It needs some look ahead, right? So in this case, it's not very appealing, right? It's not very appealing.
You don't really need an exact price, right? You just want to know if the price differential is going to be big enough.
Yeah.
To be profitable. Like, you don't care so much about the absolute value.
Yeah, exactly.
Classification problem. So
Hmm?
if you can classify at a point where it is going to go up, that's enough. You don't care.
Yeah, exactly. That's actually the whole idea.
So just a quick question, is storage only price taker?
All our study, yes. We try.
That's a big deal, right?
Yeah. Well, yeah. When we talk to battery developer, they always ask, where do I put my, what is the best location
Right.
I can put my battery? And the second question is, how do I make sure after I put my battery there, I don't kill the price piece? Like.
So I asked both questions.
Yeah.
That's location.
I always told them, right, if you give me the grid topology, I can give you some answer, but I don't have the grid topology.
I don't think it's easy to give answers, if with the topology becomes a really messy problem.
What we do know is, I have a project sponsor in Texas, and there are some company claim they sell data that with some grid topology. I think the license is $200K per year or something. Very, very good business if you claim. Yeah, if you know that data, you can sell it to all the trading companies. So battery focus on the timing of price peak and valleys. Exactly. So how do we do this? We use a decision-focused learning framework. Basically, the idea, this, if you just look at here, this is a typical price prediction, arbitrage, get your profit, right? But the idea with decision focus is we want to feed or back propagate our profit objective to our neural network, right? So the idea is we are not predicting the price to minimize the norm 2 loss function, but we predict the price so that it gives us the highest profit. In that case, right, we can model our storage arbitrage as a function of price predictions, right? And then we can define the loss function. And this is a smart predict and optimize framework. So the first author, Adam, is actually also affected here in Colombia. Yeah, the LP setting. Yes, linear programming setting. Yeah, LP. Yeah, this is LP. Yeah. So the objective is still very linear. Yeah. Have a great really and the key is to compute the grid. Yeah, so this one, right? You do back propagation, so you have it's the product of these two part of the two derivatives. This one from neural networks that's off the shelf, the key is to compute on this part, right? Yeah. So there's many different ways to do this. In the original spool framework, as smart grid optimize, there's a way to derive a upper bound, and you can minimize the upper bound. There's actually also a paper from Tsinghua on that. We tried that method, but at least on our case, in our data set, it did not perform very well in our case. So our student find another way to do it using a more intuitive perturbate layer framework to do it. Okay. So the goal is we want to predict lambda so that our arbitrage decision is close to the. So this is the realized the lambda here. Lambda head is the predict price. Lambda is the true price. So we want this two decision to be as close as possible. Okay. So we adopt the perturbate layer approach, or probably also by a 5-year-old paper from Europe, that we can add a Gaussian noise to the price prediction. Okay, and we get expectation out of it, and that can smooth the problem, right? So this is also the illustration from the original paper. Yeah, when you have a linear problem, we have polyhedron, right? If you change the parameter, you keep the feasibility region the same, but change the cost parameter in the problem. Right, if you not give, it's a linear problem, solution always land on the vertex, so you will never land anything in between. You always land in one vertex or the other. So if you think about derivative, it's basically discrete behaving, despite it's a linear problem, right? If you change the parameter a little bit, it will always give you one solution or the other, and that gives a big problem with calculate derivative. So instead, if you add a perturbate noise, Gaussian noise to the objective, it will smooth things out, and it will give us a more smooth transition. Right? So we change a little bit in the objective, the outcome will change a little bit, right? And we did prove in that paper, that this layer is convex of the price prediction and also Lipschitz continuous. That means, of course, the entire learning problem when you take a neural network is still non-convex, but at least it showed that this layer doesn't give us extra problem in the learning process. Okay. And also in practice, this is also very easy to implement. We can use Monte Carlo sampling of the Gaussian noise, it helps. And so this is also very easily implementable approach in practice, right? So yeah, so this work was done by me with a postdoc now, and the Saud is a PhD student. We test this method against a two-stage solution with RSTM and MLP, feed-forward neural network. And I will give a zoom-in figure of this. I know this much small, but basically, yes, we show that we get higher profit ratio, especially when we have low efficiency in the battery. So when basically think about this method is beneficial when the physical model becomes more restrictive, right? The higher the lower the efficiency, if you look at the ratio, we do a better job. And also the MLP network actually get better without the RSTM, because the RSTM tends to smooth the price too much. The MLP still preserves a little bit edges, right? So that's also another interesting finding. And also if you look at the optimal arbitrage decision versus the one from our predicted framework, you see ours gives the closest match, right? And also this is kind of the zoom in version of this price. If you look at it, the blue is the optimal, blue is ground truth, orange one is our predictions, and the other two are from the neural networks. You see ours does not has the best prediction, right? It doesn't capture a beautiful trend, but it does do a better job at getting the timing of the peaks. Okay, and that's really the whole idea with this
So you opened this talk by pointing out how quickly batteries are penetrating the markets.
Yeah.
So I'm curious, how stable of a training set do you need to have for this to work?
Yeah. So for this one, we train, I think, 1 year of data. Okay. Yeah, so I think this is the price dynamics are changing, and actually, yeah, that's a good point. We have a, later I mentioned we have an industry project in Texas. It turns out the Texas market pricing mechanism is changing very significantly year to year. Okay. And of course, Texas has only its own climate issue, but actually, in our current implementation in the industry project, we have much shorter training horizons.
And how much does the individual year matter? Because we have years are not representative of a stable weather pattern.
So if we are doing pure time series prediction, yeah, it's a big problem. But in practice, it turns out the most important things are the demand predictions. We need to get a demand prediction and also renewable solar wind prediction. In that case, actually, it's actually useful to observe the extreme years because that exposes how the price deviate with extreme demand and wind. Yeah. So yeah, so in papers usually we try to keep things simple. We do pure time series prediction, but later on I mentioned we have industry project. It turns out it's really about getting the best data.
So it's new, so I think you should wrap up.
Yeah, yeah.
If you can.
Actually, it's almost done.
Okay, yeah.
I think we're.
I was going to say the same.
Okay. Yeah. So yeah, real world implementation. So now it's just talking about something that we so first one is really about the bidding problem, right? How do we develop design bid, right? So now if you have a battery, you want to submit charge and discharge bid. This is a pretty neat illustration by Warren Powell from 10 years ago. And the question is, how do we generate bid? According to this paper, they propose using approximate dynamic programming. But we show if we can use our algorithm, we can already calculate the full form of the value function. It turns out the bid is very easy. The bid is just the value function. Okay, now if we go back to the objective function, take some derivative, you get this. Okay. And so this is an example that if I have this price profile, this is like the best hindsight bid for discharge and charge. You can usually see that kind of the charge here, and when you're done with price spike, the discharge bid low, and it goes up again, etc. Right? If you think about withholding, this is how exactly that we will be withholding based on the price.
But you lose and make a lot of money on those spikes.
Yeah, all the money lies in the spikes.
So this is not very good either.
And also, this also shows that because remember here, this is a function, right? This is a function. So that means the battery bid should also depend on the SOC. And this is actually one idea we talked with California ISO. Of course, we are not the only one that's mentioned this. A lot of the participants in CAISO also asked CAISO that our bid should depend on SOC, but we wrote a paper together. And last time I talked with, it used to be Gabe, and Gabe left, now is Sergio, right? He says, this is on their to-do list, but easy concept, very hard to change the market clearing software, but they said, well, who knows when they're gonna implement it? Maybe in next 2 or 3 years, but they thought that it's very complicated if they really do it. But it does show that if we have SOC ranges, then yeah, they will swing between it. Okay. And also based on this, we do have a collaboration with Concord Energy. They are developing batteries, and actually batteries there are part of their PPA, power purchase agreement, to data centers, and they actually use their battery to hedge against their forward contract risks on the spot, right? So we've been working on this for 2 years for now, and this summer we deployed our algorithm on their cloud platform. So now the algorithm is taking real data in. So all the inputs to the algorithm are real predictions. Of course, they buy their prediction from third-party vendors. So this is as our simulation, but this is really our online simulation. So now the algorithm is running on their platform 24/7, but not really controlling any physical asset. It's just like shadow operation. We see that this is one day, July 1st this year, that it does pretty well. There's 4 spikes. Right. Okay, this is perfect arbitrage. We capture all the spikes, but in our case, we capture. We missed the last one, the battery runout error, but we did capture all the previous ones. So our sponsor is pretty happy with the result, and the project continues, right? You know, with the industry project, you must be able to deliver real stuff, and they're very happy. So we are now going to do multi-service cloud management, and also they are expanding their team. So if anyone interested in doing this, is not working for us; it's working for them. Our analytics and algorithm, yeah, feel free to contact. Yeah, so that's it. So the conclusion is really market design works. It's still suboptimal, but we don't actually. The question is, we don't even know if where it's optimal. But it works. It works. Value function is really important to understand. Have an intuitive understanding of opportunity value function. I think is really important in this space, and a machine learning approach. And the price spikes is very important. So we predict prices is really about predicting price spikes in this case, not the average price. We some following up our work. We also have some separate work with market battery power monitoring, multi-market integration, and some other learning approaches. So lastly, I want to just show kind of my research group. I only talk with, but this is me and Saud, but there's a whole bunch of other people working on other topics, and also my fund agency and collaborators, and happy to ask questions.
Thank you.